I put a photo on the boards. Anyone catch it? Maybe not. It's okay. It wasn't an amazing photo. It was fine. I know you want better. So I've already pressed record, so that's a start. And let's now dig into our slides for today. Let's see here. We're gonna modify things slightly. Yeah. So first up, we are doing a profile just like we normally do. And I thought just sort of broadly celebrating microbiologists and scientists, it would be fun since, we're just opening it up to really whatever you're feeling, to do a profile on someone whose birthday is today. And that is Dr. Michael Brown. So happy birthday, Michael Brown. I don't know if anyone knows Michael Brown, but he was born on April 13th, 1941, in Brooklyn, New York, and was the eldest child in the family. He graduated in 1962 from the College of Arts and Sciences at University of Pennsylvania, majored in chemistry, then went on to medical school also at the University of Pennsylvania. He was awarded the Nobel Prize back in 1985. And so this was in the physiology or medicine category for their, in collaboration with Joseph L. Goldstein, for their work on elucidating a key link in the metabolism of cholesterol. So I figured it was also even more fitting since we just finished our discussions and conversations on metabolism. So tying that together as well. Basically, they compared a number of healthy individuals against those who have familial hypercholesterolemia, right? So metabolism, many syllable words. So basically those who inherit this tendency to have abnormally high cholesterol levels. And so this can lead to a number of problems in your arteries. And they found that this appears to be due to a deficiency of a specific cellular receptor for LDL. This is the bad cholesterol. These low density lipoproteins are drawn in based on these receptor ligand interactions, and then this helps breaks them down. But if you aren't able to break down LDL, then you are going to have clogged or narrow arteries, which can lead to all sorts of clinical manifestations and disease symptoms due to your poor circulation. So happy birthday, Michael Brown. Does anyone know how old Michael Brown is today? Any guesses? 1941 to 2021. Crunch the numbers. Boom. Oh, wow. Oh, okay. Let me check it. Here we go. Boom. Fire in the chat. Yes. I want to thank this class for teaching me how to up my Zoom chat game, because now I drop like fire and like other emojis in the chats and like other meetings, and I feel super cool. So what they say about like us teaching each other, it's true. Like I'm teaching you, you're teaching me. Like it's beautiful. It's the circle of teaching. Okay. All right. So that is Michael Brown. A few class announcements. Congratulations, everyone. I am pushing back the deadline for resubmissions and regrades until, oh goodness, sorry, Saturday, the 17th. That is a typo. Apologies. But yes, that is a typo. Check this out. See, look, what typo? 4/17/21. Okay, so there you go. I've been meeting with a bunch of students, and I know we have quite a few more meetings to go. So if you haven't heard back from me, please email me again, or if you have, please confirm. So yeah, I have meetings throughout the week with students. So please, oh wow, now the chat's blowing up. Oh, okay. I see you. I see you. All right. You're welcome. Again, at the end of the day, I think it's all about your learning, and that is your learning is not about earning a good grade, but if you're burning for knowledge, then your way is made. Oh, snap. That was like double rhyme flow. Okay, now you know if I pulled off. Your learning is not about earning a good grade, but your passion for knowledge is turning the stage. I don't know. Okay, enough of that. But basically, make sure make sure you are able to submit that by this this Saturday. Do remind, another reminder is that the practice problem for 4/8/21, so last week's practice problem, is due tonight. That is not being postponed, but also, as I was explaining to some students earlier this week, the practice problem is really about you just trying to solve it independently, right? But using resources, whatever. And I'm grading for effort, not correctness. So if you try and you put effort into it, great. If you don't, that's a problem. But give it your best attempt. And then if you don't get it right, or if you're not sure if you got it right, let's talk about it. And we can do that at success hours, which are going to be tomorrow and Thursday. So there will be no success hours on Friday. So I've had a number of requests for Wednesday meetings, and so it looks like there's high demand for Wednesday. So I'm trying to meet the needs of the class. If you prefer Friday, please email me. I think I have 2 more slots left for Friday. So these are going fast. A lot of regrades are happening. That's totally fine. That's why they're there. But please email me so we can figure it out. All right. And then finally, please, whoa, that is Melissa, I don't know what that typing thing is, but it looks cool. I just don't know what it is. So that's great. Are those 2 people? I don't know. All right. Oh, wow. Okay, great. Learning new things every day. So the exam unit 3 is next week. This is the 1 week heads up. It's going to be this exact same style and structure, but the content will be from everything since the last exam. So please let me know if you have questions about that. And then lastly, brief plug for COSAC, College of Science Advising Center. Probably heard of that. They're hiring. So if you're interested in tutoring, helping others, this is a great opportunity to make some money, and you can apply online. There is the link, and you can also email the Science Tutoring Center at sjsu.edu for more information. All right. Are there any general questions from the class? Any general questions? Going once, going twice. I think their schedule is pretty flexible. I believe it or not, Martin, I have not been a tutor for Kozak, and I know that's going to come as a shocker, but yep, I know. You thought I'd done it all, but I definitely missed out. So that is, I think, a great question for Kozak to answer. Although it's possible someone in class knows. Oh, did I tell? No. Okay, no, I had. Yeah, I was making sure I had all the reminders in there. Okay. Okay, great. Then off we go. All right, and savor these moments. I know some of you are feeling like, oh my gosh, like Dr. Adams, I just want the semester to end right now. Like that is how I feel in my soul. But once the semester is over, you won't get this anymore. All right. You won't get this amazing time with really bad puns. So just savor it, because oh no, don't know what you got till it's gone. And paved over paradise to the parking lot. Okay. Clearly I need to listen to that song again because lyrics are not there. But what am I teaching next semester? This is a plug for 141 if you're interested in that. So I'll be teaching 141, and then I don't know actually. But yeah, come check out 141 if that's your thing. Okay. And yeah, if I find out more, I'll let you know. So now we're shifting gears a little bit, all right, to talk about the beginnings of microbial life. So how cool is that? I think it's pretty cool. Where it all started. And basically, when you think about microbial life, we're thinking big picture just a long time ago. We're not talking last week. We're not talking, cavemen. We're talking the very, very beginnings. And hopefully through both the reading and today's class, as well as the next class, we will make these connections about some of the driving forces that led to the creation of the earliest cells, as well as implications for how things diverged, right? And what mechanisms pushed forward these processes. And I was going through the chapter, and I was getting all nostalgic for the beginning of class, because I remember like one of our first classes was like, oh, like, don't you want to talk, like, what are your questions about microbes and stuff? And we were talking about microbial evolution. I don't know if anyone remembers that. And I was like, oh my gosh, like we'll get to that like way later in the class. But now we're here. Actually, I think we'll get to that specific question next class, but we're basically here. So pretty cool. So when we think of these origins, there are certain fundamental conditions that were required. And I wanted to see, does anyone have a guess as to what some of these conditions were? Some of these early conditions for cells to exist. And you can share via the microphone. I'm not wearing headphones anymore. Those days are probably behind us, but yeah, or you can type it in the chat. What are some of the conditions that were required? A food source, maybe water, maybe. All right. Oxygen, interesting. Gases, all right. Okay, so carbon source, All right, so I think we're getting at some big picture principles here. So essential elements, all right. You need some building blocks, and my favorite building blocks are Legos. Just, obviously, what better building blocks could you want? Um, and so you have these different organic uh, molecules or material that you can use to assemble things. You need an energy source, all right. So I saw some answers talking about, uh, light or food source, right? You need some kind of energy to power reactions, right? And this mainly is driven through nuclear fusion within the sun, all right? And last, but certainly not least, you need a temperature range permitting liquid water. And so this is really important and really tricky. And it's sort of what has made the hunt for a life so challenging, trying to find conditions that allow for um, liquid water. So you don't want it too hot, and you don't want it too cold. You want it just right. Um, that perfect Goldilocks bowl of porridge or oatmeal or soup, whatever it was just right. And you needed the metabolic reactions to take place in that environment, right? You have this fluid environment, literally. Without that, you're not going to be able to have those interactions, and that would lead to a cease in, the development of life. And so scientists and researchers have been looking at evidence of life for a while, and looking at different indicators or signs that life could have existed. And one of the earliest forms that we have clear fossil evidence for is these bacterial communities called stromatolites. And what you can see here, and what your book talks about in some detail, are that they have been able to identify these masses of limestone, right, and calcium carbonate formations that are approximately 3.4 billion years old. And this exploration of really old rocks, right, is one way that they're trying to connect modern day microbial mats to ancient patterns that resemble them. And you can see that in these two photos here, you're comparing modern day microbial communities that can create these patterns that are very reminiscent of these ancient rock formations that have been uncovered. And by looking at these two together, you could say, hey, there's some strong similarities here. And while this is not rock solid proof, if you will, it is suggestive of these that microbial activity was occurring at a very ancient time. Now, when we think more broadly about these major elements of life, there are biomolecules that were formed through a series of nuclear reactions with stars. And this figure highlights the schematic of stars that explode into supernovas and before the birth of our own solar system. So you have this cycle that a massive star will undergo, and that can contribute to a huge amount of energy that is released. And that can power a number of processes, the most important of which are ones that can drive reactions that eventually lead to the formation of life as we know it. And so I think what the book does a good job of explaining is sort of taking this big picture approach and then narrowing in on specific models and theories. And so here in these initial slides, we're talking more about solar system formation and how individual planets start to coalesce, right? This is very big picture, but then we'll see how these different forces interface with one another. And then we start to zoom in more on how the formation of our own planet provides an environment that is relatively hospitable for the development of microbial organisms. And so I think this is probably familiar to most of us, but our Earth's composition consists of the core, the mantle, and the thin outer crust, right? And you can see these distinct layers in the schematic to the right. The core and mantle are rich in iron, and this is differentiated by the crust, which supports the biosphere and basically all life on Earth, right? We don't have a bunch of life, not that we know of, that can survive the mantle or core of the Earth, right? The environment that is conducive to some of these initial properties we talked about in the first slide would be our biosphere on the crust. And the crust itself is able to generate electron acceptors, most notably oxygen. And so we have these different clues as to what exists for, or when early life might exist. And I'm curious if anyone knows what clue this might be for life on Earth. What would we call this clue? And to guide the class a little bit, evidence for life in the geological record is called a what? Fossil? Okay. This particular one is called a biosignature. Get it? Because it's bio in a signature form, or biological signature. Just trying see creativity, right? Just a little spice, just a little throw it in there. You gotta pay attention to catch them though. All right. So biosignatures are distinct than fossils, as they've been found, and they're also even found earlier than the oldest fossils. However, it's hard to know their exact significance because biosignatures are thought to, while they're thought to be created from microbial processes, it's hard to know for sure if there are non-biogenic explanations. And so scientists and researchers will try to corroborate these biosignatures by finding independent scientific theories or laws that would further validate the likeliness that they arose from microbial processes. So this area of research is, by its very nature, a little controversial because of this tension about is it possible to recreate a biosignature or evidence of a biosignature through a non-biogenic explanation. And so as we walk through time today, we will see how different pieces of evidence appear during different ages or eons of life, okay? And so the first period of Earth's existence is from 4.6 to 4.0 billion years ago, or gigayears. So the abbreviation GYR, hopefully you caught that in the book. That's not like, that doesn't stand for a gazillion years, it's gigayears, right? Which is interchangeable for a billion. So 4.6 to 4 billion years ago, the Hadean eon existed, right? And this is the earliest time of Earth's existence, or as some of my friends would say, these are early days. And this is where you have, like, you don't want to be around during this time. Basically, you're like, if Earth is the worst dodgeball player, then like that's what's happening, right? It's just getting pelted with dodgeballs or meteors. Dodgeballs would have been nice, but just getting nonstop meteor bombardment. And so Earth is trying to like arise during this time. Life is trying to arise on Earth, and it's just like meteors like nope, 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 right? And so it's rough. It's rough. I'm glad I wasn't around then. This is not my scene, and I love dodgeball, right? But that's the stakes are a little too heavy there. All right. So basically, you have meteoric bombardment, then this continental crust is formed, and this formation then leads to the first sort of possible time where you can get this microbial establishment on Earth's surface. And this transition allows us to enter the Archean eon. And this is approximately from 4 to 2.5 billion years ago. And that is where you have the strongest geological support for the earliest possible time of life arising. And that's directly related to the decrease in meteor bombardment, stable oceans, as well as these stromatolites that we have uncovered at different sites around Earth. And so you start to have these small indicators that life may have actually arisen, right? And then the evidence only becomes stronger as you move forward in time, right? Eventually you get to us and you're like, well, I'm pretty sure we're alive right now, but who knows for sure, right? And so this transitions to this criteria of microfossils, okay? And these are very striking because of their visual appearance. However, they can be controversial because they are unable to truly incorporate quantitative criteria. And so, again, you have ranges for all these different systems, right? Or pieces of evidence. And approximately 2 billion years ago is the earliest time that these microfossils have been dated. And this includes a combination of both filamentous prokaryotes and colonial cyanobacteria. And they become more common the more recent you go through the Earth's time period. Here are some examples of the microfossils that the book highlights. And you can see, right, if you look, you just do sort of a comparative analysis of structures and morphologies, the patterns and the similarities between modern day microbial species and the microfossils that have been isolated. And so just by sort of looking at them from a qualitative perspective, you're able to see these similarities, and they are suggestive of ancient microbial life at least existing. But they can be controversial as well because researchers can then try to disprove this by generating similar morphologies and shapes through abiotic processes and chemical reactions. Okay, so that again sort of hints at the underlying tension in the field. Is there a way, this is a question for the class, is there a way to 100% prove that microfossils cannot be made by abiotic processes. And I can type this in the chat. Is there a way for scientists to 100% prove that microfossils can only be made by biotic processes? Any thoughts on that? Hello? Hello? Is anyone there? Am I disconnected from the Zoom meeting? Come on, Micro 101. I believe in you. Wow, thought it'd be fun. No, I promise this is a genuine question. This is a genuine question. It's not a long pun to stun the fun of Micro 101. Yeah, I can fake it. Okay, Dr. Seuss. Right. I don't know how you could do that, right? Like you can continue to add evidence to build your case, but like there's an infinite number of abiotic processes going on, right? I don't know how you could ever test every single one to actually prove it's only biotic, right? And so I think it's important for us as scientists to realize that while we can show a lot of support for different things, we also need to recognize the limits of science, and science is not always going to be able to give us the answer we want, but the power in science is that it's objective, right? And so I think it's still a very strong statement to say that it's most likely caused by biotic processes if no abiotic processes have been shown to make these specific shapes or morphologies, right? So something to reflect on as we continue through these different types of evidence. And so you can also extend the analysis that you perform on microfossils by combining that with these image analyses with more more recent technologies, and this includes Raman spectroscopy, which basically measures energy levels of laser light scattering. Okay, and you can use specific laser wavelengths to see their shift based on the presence of carbon bonds that exist. And basically what this is, that's ramen. Wow. I thought that was a ship for a second, looking at the chat. And so basically you can look at these characteristic, look for the presence of carbon bonds, and that is evidence of organic material that correlates with the shape and size of the microfossils that you've identified. So taken together, this adds another layer of evidence in support that the microfossils are actual evidence of early microbial life on Earth. Now, likewise, you also have isotope detection mechanisms, and we'll be talking about that in the upcoming slides. but basically looking for the presence of specific isotopes and the depletion of others is really important for navigating the other line of reasoning for this fossil analysis. And specifically, that means we're looking at the depletion of carbon-13, because as we will discuss further, microbial life is able to preferentially select for carbon-12 atoms as opposed to carbon-13 atoms. So if you see a lack of carbon-13, then you can use that to strengthen your argument that microfossils are actually, again, the evidence for this early microbial life that was incorporating carbon-12 into its cellular structures. So in this way, you have multiple lines of evidence intersecting to make the case that microfossils are, in fact, well, if we'd been there at the time, we would have been able to detect this microbial life with a microscope. And if you'd like to know more about the NanoSIMS technology, I include a link at the bottom of the page. So looking at isotope ratios, right? They're defined as a quantitative biosignature, okay? And this is powerful because, you know, now instead of doing this sort of subjective analysis, just looking at a picture of a microfossil or like a old rock and wondering, did a chemical reaction make this? Did a long dead microbe make this? We can actually analyze in a more objective manner what is present from an isotope level, okay? And so I've shown the atomic makeup of the 12 carbon atom, or carbon 12 atom and carbon-13, not 12 carbon atom, that doesn't make any sense. And you can see that the difference here is in the number of neutrons, and enzymes, right, present in different microbes have been shown to have a preference for carbon-12 over carbon-13. And this is useful when we think about the process of carbon fixation. And we haven't really had a chance to talk about this too much in this class, but I think your prereqs have probably touched on this before. But basically, carbon fixation is where you are taking carbon from the atmosphere and fixing it into a solid substance, such as a rock, or as this process utilizes carbon dioxide to calcium carbonate. And because enzymes prefer carbon-12 over carbon-13, if there are microbial processes that are active, right? If microbial life is taking place with these enzymes, then we'd expect there to be more carbon-12 than carbon-13. And put another way, you could say that carbon-13 would be depleted in the microbial specimen compared to carbon-12, because the enzymes are picky. They're like, I want carbon-12. And then again, it's like, I want carbon-12. And it keeps passing carbon-13. It's sort of like when someone offers you chocolate cake or lemon cake, right? Like, there's nothing wrong with lemon cake, but obviously you're going to choose chocolate cake every time, right? Like, I think we're all on the same page there. If you like lemon cake, please see me after class, or more than chocolate cake, then, I mean, look, we'll talk, we'll sit down, we'll talk through it, we'll get through it. But there's a distinct advantage to a 5-layer triple fudge chocolate cake. The lemon cake, it's just not going to do for you. And likewise, these enzymes are preferring carbon 12 over carbon 13. And we can use this preferential selection to our advantage. So let's do a eye clicker here. I apologize, I forgot to set that up. But really quickly, we're gonna switch back in a second. But basically, I want everyone to go ahead and think about the following question, which is shown on this screen here. Sorry, one second. So, yeah, go ahead and get your eye clickers activated and ready. And basically, this is carbon fix this. The calcium carbonate deposited by carbon dioxide fixing autotrophs should contain blank carbon 13 compared to calcium carbonate deposited by abiotic processes. All right. So is it A, more, B, less, C, the same, D, double the, or E, cherry flavored? And the answer may surprise you. So go ahead and think about that. I also believe it's in your slides. So again, I'm gonna stop share and load up the iClicker cloud. Again, apologies for this oversight. And class should be started. So go ahead and log in there. We'll return to the screen one last time. But do we think it should be A, more, B, less, C, the same, D, double the, or E, cherry flavored? Go ahead and enter your answers, and I'll give everyone a minute. I know this is last minute, if you will, but go ahead and enter your answers, and then we will see how we do. For those of you who've already answered, I guess I'll share that yesterday I actually met another microbiologist, and they were bigger than I expected. Does anyone get that? There you go. There you go. If you wanted puns, you now have them. That joke is actually not mine. It's not mine. An employee at San Jose State, an administrator gave that to me. So I may reveal their name later, so you can take your complaints or compliments to them. All right. So time is up. Let's see how we did. Okay. So that is interesting. Let's talk about this. This is why we do eye clickers. Okay. So basically, unless you chose double the, everyone had a vote. I'll do a little spoiler. It was not cherry flavored. Let's walk through this as a class. What are we thinking about here when we are trying to navigate this question? Someone explain why they chose the answer they did. Just think, you're asking me to write your letter of recommendation, and in this moment of silence, I'll remember that this person was like, the reason is because of this. It makes a very powerful statement. Not that you're doing it just for the letter of recommendation, but no time to shine like the present. I thought autotrophs would prefer C12 because there would be less C13. Therefore, there would be less C13. All right. Thank you for sharing, Domini. Sarah's chiming in. Biotic processes have more carbon than abiotic. Sarah, to clarify, you're going to need to specify what type of carbon, right? So that is a distinguishing factor. Are people agreeing with Damini? Are they? Harpreet agrees. Okay. Anyone else want to push back here or chime in with another perspective? All right, a lot of consensus building around Damini's initial statement here. All right, well, let's walk through it together and see if Dr. Adams agrees with Damini. All right, because I get to say something too. So people are students like, all you do is say things. Ugh, the worst. All right, so here's a little schematic I made. All right, so we're thinking about two processes. All right, autotrophs and then abiotic processes. Autotrophs have enzymes. We know that these enzymes prefer carbon 12 over carbon 13. That means there's going to be more carbon 12 and less carbon 13, right? If we compare it to abiotic processes, right, they have no enzymes, so there's not going to be any change in these ratios. So relative to the carbon 12 present in abiotic processes, you're going to have more carbon 12. Relative to the carbon 13 present in abiotic processes, you're going to have less carbon 13. All right. So let's go back to our question. The calcium carbonate deposited by these autotrophs should contain blank content of carbon 13. Well, based on a little chart, it looks like it should be less. All right. Not more and not the same. And unfortunately, not cherry flavored, although I can't rule it out explicitly because I have not tasted it. But let me tell you, if it tastes like cherry, these autotrophs are in trouble because that is delicious. I should have done chocolate flavored, huh? All right, well, next time. Although chocolate cherry cake, let me tell you, that is trouble. Kevin is asking, where did it say enzymes prefer carbon 12 over carbon 13? Well, enzymes prefer carbon 12 over carbon 13. We're going to do that right here. Sorry if anyone missed that, but let me just do a where's Waldo moment on that one. All right, so there we are. Good in case, comes up on the test, hypothetically. So hopefully we're now all on the same page there. And we're going to jump into a little bit of the nitty gritty in terms of calculating carbon isotope ratios now, all right? To really get comfortable with this, we're going to sink our teeth into some rocks so we can study the isotypes, okay? So all right, I'm not even going to try to trick the class on this one. I literally just thought of this joke. But if you have like two rock types, or you have two different rocks and one is very different in their carbon makeup than another, the first rock will say to the second rock, "You're so not my isotype." Isn't that hilarious? Oh my gosh, science is the best. All right. So, okay, now we're going to calculate some carbon isotype ratios. Basically, we're trying to figure out the delta here. All right, the delta in terms of the amount of carbon 13. All right. Why are we doing this? Because based on the previous question, all right, the amount of carbon 13 is going to change because some enzymes have a preference for certain isotypes of carbon, all right? So enzymes want more carbon 12, thus there will be less carbon 13. And so there's this basic equation right up here. Yeah, I like the circle. I'll square it. Dr. Adams is such a square. Okay, so, well, I guess it's a rectangle. Sorry. All right. All right, so you have this equation, all right, and you basically get the isotope ratios of carbon 13 and carbon 12 from your experimental sample. And then you get your isotope ratio from your standard, okay? And then you divide it by your standard, and then you multiply it by 1,000, all right? And so basically, I'm going to walk us through an example of this happening, all right? So this slide is actually really full of puns, right? Because your experimental it's like random rock, right? So you know that random rock group your friend likes, but no one else really likes, right? Like that's the rock. No, we're talking about like a rock on the ground. So you get like, you get this old rock, right? And then you measure the isotope ratios. And then you compare it to your standard rock, like your standard classic rock, like just 80s classic rock. All right. So like that's your standard rock. And then I don't know, maybe like Led Zeppelin or something, right? I'm not gonna ask if you know who Led Zeppelin is, but we'll just assume everyone does and it'll be a safe space. All right. So you insert the values, right? So first you put the value in for carbon 13 and for carbon 5, right? And so, sorry, carbon 5, carbon 12. Then you do it for your standards, right? And then you just plug these values in, and then you generate, you go through the math, and then you get the change in carbon 13, okay? And if you're wondering where did I get these numbers from, like I'm not going to ask you to go out and like actually do the isotopic measurements. I would provide you these numbers. So you'd get a table with some numbers, you plug them into this equation, run through the math, and then, or walk through the math, whatever you're, stroll through it. And then you'll get a carbon value, okay? Or carbon 13 delta. And this delta reflects a huge difference between the experimental standard or experimental sample and the standard. Because remember, all we're trying to do here is compare an old rock versus a standard rock, okay? And the standard rocks are a reference for us to determine are abiotic processes occurring or are microbial processes occurring. And so the bigger the delta 13 is, or sorry, the delta in the carbon 13 is, then the more likely, the stronger the evidence is that there was was evidence for the abiotic processes, okay? And so I think you'll see what this means in a little more context in just a second. So let me go ahead and go to the next slide, okay? Whoa. Okay, so 1 second here. All right, so basically this graph is looking at isotope depletion, okay? And so if we are going to look for evidence of organic material and microbial activity, then we want to have a reference and then look at these different delta carbon 13 values. And so the depletion of carbon 13 generates a large negative carbon 13 value, and accumulation generates a positive value. So what this means is that the larger the negative value, then the less carbon 13 is present, and thus the more microbial processes are occurring. So to write that out, the larger the negative carbon 13, then the less carbon 13 present, which means the more microbial life. Okay, so I'm gonna put that right there, and I'm gonna check the chat. Right, and so I know this field is amazing to me for a number of reasons, because you literally have these standard rocks that serve as like references, where there's basically this is basically serving as like an objective measurement for where microbial processes are not taking place, but there isn't like a emphasis on abiotic processes, right? It's basically references that provide this dividing line between enhanced abiotic processes and non-microbial processes. And because I'm curious about, I'm just curious enough, not curious to study it, but curious enough to understand it, they actually publish like international references. So I included one here. It's called the Assessment of International Reference Materials for Isotope Ratio Analysis. It's a technical report, surprise, for pure and applied chemistry. Okay, and here's the hyperlink to it, so you can check it out. If you find this stuff fascinating, great, because that will take you all the way to the minutia of how these references work. But for the purposes of this class, what you're going to be responsible for is understanding how to generate these delta carbon 13 values when given different isotope ratios, and then understanding that the larger the negative difference, the less carbon 13 present, and the more microbial price that exists, or life, not price, microbial life that was likely to be present. Okay, so I ran through quickly another example to calculate example B. Okay, but the answer, just to hop back to that very briefly. Whoa. Why won't this erase? Let's see. Okay, sorry. So here, okay, again, same equation, but if the experimental isotope ratios are the same, the exact same as the standard rock, right? Then they're gonna subtract out and you get 0, right? And if there's no difference, then you'd be right on that line, right? There'd basically be no evidence for these microbial processes taking place, right? It's the exact same as a standard reference rock. And of these two samples or examples, example A is more likely to have microbial life present, or is stronger. Example A is stronger evidence for supportive microbial life at based on the isotope ratios. Okay, so one more time to drive it home. The larger the negative value is for carbon-13 deltas, then the less carbon-13 is present, and the more likely likely microbial life was present in that sample. So go through that. I know it is a little number heavy, but hopefully that makes sense. I am going to pause here to see if there are any questions on that concept. And you can ask them on the microphone or via the chat. Some people are like, I prefer punk rock like Blink-182, so thanks. All right, I see no further questions, so we'll keep going. Other biosignatures include some chemical signatures, such as hopanoids that are produced by cyanobacteria, and I've included a paper on these as well in case you are curious about learning more. These are steroid-like membrane molecules that, because of their durability, can still be detected in certain rock samples. And there are other signs that we can use to understand evidence for microbial life, specifically banded iron formations. And this is indicative of the presence of oxygenic phototrophs, which are basically cyanobacteria species that are able to split water to form oxygen. And this is notable because this evidence for oxygen is particularly strong when we look at oxidation states of different minerals, particularly iron oxide, and the layering that is present in very old rock formations, which are referred to as banded iron formations or BIFs. And these are present across the world and basically consist of gray layers of silicon dioxide and then alternating layers of iron oxide that again can be detected in these very old rock formations. And because we see this banding pattern, it suggests that there were wildly fluctuating levels of oxygen in the atmosphere. And so you could think of the first cyanobacteria that are able to split water into oxygen, and this leads to an increase in oxygen. That oxygen is then consumed, and then you could have all the oxygen used up, right? And so you have oxidation of iron that is deposited as sediment, and this process can then recur until other chemical reactions lead to a more stable environment for oxygen to be present for a longer period of time, right? And this is a process that was just naturally part of Earth's evolution. And the schematic here shows this sort of banding pattern occurring in more detail. Basically, you have the upper waters getting this influx of ferrous iron that then is oxidized to ferric iron. And you can also get the sedimentation that is occurring that in part can be driven by this photosynthetic iron oxidation. And it is thought that these sort of ancient microbial processes then led to these alternating banded iron formations that we see today. And I know we've covered a lot of different types of evidence for the beginnings of microbial life. And this chart I like because it ties in a lot of the timelines for the different pieces of evidence together. And so I think, if you're trying to connect everything in terms of the chronology, this chart does a nice job of helping us see some of those pivotal pieces of evidence in a chronological fashion. So let's see how we're doing on time. We're gonna keep moving on, but I think a good reflection question that I encourage you to think about. I'm not going to collect it or for credit, but a good study question would be ranking these different pieces of evidence and then seeing what piece of evidence would rank the strongest versus the weakest based on some of the pros and cons that you could think of for each type of I guess, how do I want to say this? Each type of approach or set of data that you have, right? So you could have a set of data for microfossils, you could have a set of data for biosignatures, etc. How would you rank these, and what would you use to justify your ranking? Okay. But in the interest of time, we're going to move on. Also, that's a rock solid, it's a pun, rock solid evidence. Hey, okay. So we're going to now continue on to early metabolism in the life of microbes and the life on Earth. And I know some of you thought, oh, I thought we left metabolism behind. Well, it's back, but in a very, I don't know, broad strokes manner. Here, we're just briefly discussing some of the metabolic reactions that occurred in some of the earliest machines. So we have anaerobic oxidation reduction reactions. And this is where you have molecules that were generated by reactions driven by UV light. Okay, so this is one set of reactions that would occur before oxygen, right? So I know we just talked about oxygen, but metabolism was still going on before oxygen, right? We've talked a lot about how there are different strategies for generating energy, and anaerobic metabolism is one set of these reactions. Before oxygen, you also had light-driven ion pumps, okay? And so this is how you can power specific membrane pumps that are present in different archaea and could have led to the first kind of autotrophy, right? So you're getting that energy from light and using that to power your pumps to generate membrane potential. And then you also have methanogenesis, right? So this is a very specific set of metabolism that's based on methane and the conversion or the combination of hydrogen and carbon dioxide molecules, right, which leads to the generation of methane and water. And so there's evidence for methagenic archaea that will use this process to generate energy to carry out their microbial processes. And so in relation to this, right, you have metabolism models that are in the absence of oxygen, but you also have a number of different models for how non-living materials were able to replicate, quote unquote, and evolve, right? So you don't have bacteria yet, but they had to arise from something. So what would they arise from? And there are three basic models here. You have the prebiotic soup, all right? It's sort of like chicken soup, but without the chicken. You have metabolist models, okay? So that's not surprisingly metabolism based. And then the RNA world, right? That is also not surprisingly based on RNA. The prebiotic soup model is soup or cool because you have these small organic molecules that are thought to have risen abiotically and as a result from this sort of self-organization through compartmentalization. And this is also thought to have been assisted with lightning. And basically, you can have these hydrophobic and hydrophilic interactions that lead to the formation of compartments. Okay, so you could have them spontaneously disassembling and assembling. And you know, just this structure right here is reminiscent of a cell, right? It's reminiscent of a very primitive cell. And this could, in theory, continue to lead to larger aggregates and complex macromolecules that allow for a fully compartmentalized membrane with compartments inside it. And while I want to talk to you more about the other models, that means we're going to end on a cliffhanger today, class. So hopefully you can wait till next time, but if not, come to office hours or success hours tomorrow, and I will give you a sneak peek. Also, it's in the text. But thank you for your participation. Thank you for laughing at a couple of the puns, and I will see you, if not tomorrow, on Thursday, and take care.